Quick, graph y equals the opposite of the sine of x by hand two different ways. We're also going to compare and contrast graphs and equations and look for patterns in these equations here. This is the part of the family of functions series. You will need paper and straight edge, and we suggest you create grids similar to the ones at the right as needed. Press pause as needed anytime during the video. The first way is with the sine dance. Recall the graph of y equals the sine of x, one period or one wave, and notice the 5 key points of interest. These key points are affected by the parameters in the equation, as all the points are, and the only parameter we have is the opposite outside the function. That opposite sign takes the opposite of each y value, leaves the x values alone. The initial point, the origin, is unaffected because the opposite of the y value 0 is 0, so we'll plot the origin 0, 0. The point at the end of one period is 2 pi, 0. This is also unaffected by the opposite sign. The opposite of 0 is 0, so 2 pi, 0. And the halfway point between these 2 points of inflection is another point of inflection, usually at pi 0, and again unaffected by the opposite sign, so also at pi 0. Halfway between the first 2 points of inflection is a maximum, normally at pi over 2, 1. However, the opposite sign reflects the point to pi over 2, -1. Halfway between the second and third points of inflection is a minimum, normally 3 pi over 2, -1, but this one's going to take the opposite of the y value, 3 pi over 2, +1. Pause is needed. Here we're going to connect the points as a sine wave, but reflected about the x-axis. So we'll have a smile first and then a frown, instead of a frown and then a smile. This is one period of the sine wave. We're going to duplicate the wave to the left. So we're going to go back a period, which is 2 pi from each point, especially the key points. And again, we can connect these as a sine wave, but again, reflected about the x-axis. So concave up, followed by concave down. Comparing that to the parent function, this is y equals the opposite of the sine of x. In blue, here's the y equals the sine of x. We also put a dashed line at the x-axis because, as you can see, these two graphs are reflections of each other about the x-axis, mirror images, if you will. They are also reflections of each other about the line that contains the points of inflection, because that x-axis in this case contains the points of inflection for both graphs. Pause is needed. Second way to show this is using a table. So let's go ahead and graph the sine function in blue here, complete the table. And these are our axes values. We need to create a second table for the opposite of the sine of x. We're going to need to take the opposite of each y value while the x coordinates are going to stay the same. So let's just go ahead and put those in there. And now one by one, we'll take the opposite of each y value. And the opposite of 0 is 0, so we start at the origin. The opposite of 1 is -1, so pi over 2, -1. The opposite of 0 is 0, pi 0. The opposite of -1 is +1, so 3 pi over 2, +1. And the opposite of 0 is 0, 2 pi, 0. We'll connect the points as a sine wave, but again reflected about the x-axis, so a smile concave up followed by a frown concave down. This is one period of the wave. Let's plot another one to the left by going back 2 pi from each of the key points, because 2 pi is a period for this. And again, we'll connect the points as another sine wave, but reflected about the x-axis. Smile, then a frown. And comparing that to the parent function, again, we can see that this is reflected about the x-axis. Now let's investigate an extension of this idea. On the next page are pairs of graphs. We're going to compare and contrast the graphs and the equations, and we want you to look for patterns. So here we have two pairs of graphs here, a blue and a green and a blue and a green. Pause to compare and contrast them, look for different patterns. Pause is needed, resume when you're ready. So it turns out that the equations are identical except that one has a positive coefficient and the other has its opposite as the coefficient. The graphs are reflections of one another about the line that contains the points of inflection in both cases. So there's patterns going on here. Again, here's another two pairs of equations and graphs. Pause to find some patterns. Again, the equations are identical except that one of them is a positive coefficient while the other one has its opposite as the coefficient. Here we have the 2 and -2, and over here we have the 4 and -4. We can also see that these graphs are reflections of one another about the line that contains those points of inflection. Pause is needed. So how can we use what we just discovered? When asked to graph an equation with a negative coefficient for the sine term, graph the equation with a positive coefficient first, and then reflect that graph about the line that contains the points of inflection. That's what we're taking away from this. So you can see at y equals 2, these are reflections of one another. We suggest that you write this down, but that's up to you. Pause is needed. Now you try one. Given the graph of y equals 3 times the sine of x plus 1, on the same pair of axes, graph y equals -3 times the sine of x plus 1. Pause to do this, resume when you're ready. First, we draw the line of reflection, and this goes through the points of inflection. Then we're going to reflect the points of interest about this line. So here, the points of inflection stay where they are. The max reflects to a min, the min reflects to a max. And then we go ahead and connect those points using the green graph here. And you can see that these two graphs are reflections of one another about the line that contains the points of inflection, the line y equals +1. Now we'd like you to try another one. Given the graph of y equals 3/2 times the sine of x plus 2, on the same pair of axes, graph y equals -3/2 times the sine of x plus 2. Pause as needed. Again, we first draw the line of reflection, and this is the line y equals 2. That's the line that contains the points of inflection. So the points of interest, again, the points of inflection stay where they are. The max reflects to a min, the min reflects to a max. And then this is the graph in green. Again, notice that the two graphs are reflections of one another about the line containing the points of inflection, the line y equals +2.